got one last topic for you, and it's called the sampling theorem. And this is the thing that will probably blow your mind. If you've got a continuous time waveform here, here's your x of t, how many samples of that does it take to be able to perfectly, not approximate it, but perfectly replicate it?
Infinite, sir.
Yeah, you certainly think so, right? How about if I said, I'm only interested between the time period 0 to 4? How many samples would it take to perfectly replicate that signal exactly?
Still
Sir,
infinite.
Here's the part that's not obvious. You actually don't need an infinite number between 0 and 4. In fact, you can perfectly capture all signal information, not in any kind of in the limit as, but exactly if your sampling frequency is greater than or equal to 2 times the maximum frequency of your continuous time signal. This is what the sampling theorem is. There's a word for this, 2 times the maximum frequency of your continuous time signal. It's called the Nyquist frequency. So as long as you're sampling above the Nyquist frequency, you have no information loss. If you don't do this, you have aliasing. And again, aliasing is when high frequencies look like low frequencies. We saw this in this example here where a high frequency of 2.6 pi looks like a low frequency of 0.6 pi. But now we're talking about something slightly different. We're talking about going from continuous time down. And that's why if you want to sample continuous time down, you want to always firstly put it through an analog anti-aliasing filter, it's called, e.g. 20 hertz. And then you're going to sample it. And if this doesn't let anything bigger than 20 hertz through, then you could sample at a sampling frequency of 40 hertz, twice the highest frequency that's here. And now you'll have an X of n that has no aliasing at all. If you want to leave right now, you're more than welcome to. I've created a MATLAB demo that shows this intuitively. And it'll just be a moment to show you that. Okay, here's a MATLAB demo. I've got it out uploaded on my website if you want to play around with it. In blue, it shows the original continuous time waveform. In black, it shows what that looks like if it's sampled at 10 hertz. So right now we're sampling at not just twice the original frequency, but at 10 times the original frequency. So we've got a nice small omega, discrete omega frequency of pi over 5, and everything's fine. What happens when we start to lower our sampling frequency? It's even here with a sampling frequency of about 8, it's still, everything still looks fine. But what happens if we go down radically? Now we're still sampling it over twice, but it's not by much. You can see our discrete frequency is rising as we sample it at a lower rate. And once that discrete frequency starts to go to pi, starts to get up to pi, we're in trouble. So now we're at the point, we go over to a discrete frequency, a sampling frequency of 2. Now you've got a sampling frequency of 2. Our omega discrete is equal to pi. This is the highest possible discrete time frequency we can have, where it alternates phase by 180 degrees every sample. If we were to reconstruct it in red, we'd still be able to reconstruct the signal. But now, as we lower our frequency, I'm going to get rid of the reconstructed signal. As we lower our sampling frequency, can you now see that our reconstructed signal would look, I'm going to go still further, make it clearer. Yeah. Now look at what our reconstructed signal looks like. That's called aliasing. The red signal is our best guess of what the original signal looks like. And as we continue to go down and down, eventually, now you can almost see with your eyes what that reconstructed signal would look like. It's starting to look like almost zero right there. Or it's pretty darn close to 0. And if we continue to lower our sampling frequency, it's going to seem like it picks up in speed again. If I get rid of this, you can see that underlying sinusoid. This is what happens when you take a look at a fan in front of a computer monitor and the fan looks like it's speeding up and then slowing down. You take a look at an engine propeller, a plane's propeller, and it seems like it speeds up and then it slows down. It's because your eyes are sampling it. Or wagon wheels in an old Western movie that seem to speed up and then slow down even as the wagon is accelerating. That's because the movie is sampling it at about 24 times a second.